This tutorial discusses half-life of reactions. A half-life is the time it takes for half of a sample's concentration to disappear. For instance, if we start off with 1 molar and we want to go to half that amount, which would be 0.5, that would be 1 half-life. After 2 half-lives, it cuts that 0.5 down again to be 0.25, and so on and so forth. For first-order reactions, the concept of half-life is especially useful. For a zero-order reaction, the lower the initial concentration of the reactants, the shorter the half-life. For first-order reactions, the half-life is independent of the concentration. Notice that it's ln of 2. So the fact that there's no concentration written here means that it's not relevant. For a second-order reaction, the half-life is inversely proportional to the initial concentration. Increasing the initial concentration shortens the half-life, because it's 1 over it. So as this number gets bigger, the total half-life gets smaller. So let's do some practice problems with these. Molecular iodine dissociates at 625 Kelvin with a first-order rate. That's important because that's going to tell you which one of these to use. First order is right here. T of 1/2 is equal to ln of 2 over K. The rate constant, which is the K, is 0.271 as to the minus 1. What is the half-life of this reaction? So, T of 1/2, this ln of 2 can be put into your calculator, and it will always come out to be 0.693. Divided by the rate law, or the rate constant, and that comes out to be 2.56. Because the rate is in per second, that means that's how many seconds there are. Sucrose decomposes into simpler sugars of glucose and fructose as a first-order reaction. So that's the one with the natural log in it. Its rate is a disappearance is given as sucrose is equal to the rate constant times the concentration of sucrose. So let's try some practice problems with these. If the rate constant is 0.21 per hour, and sucrose's concentration is initially 0.010 molar, determine how much time passes so that the sucrose's molarity decreases by 90%. Alright, so if we're talking about 90% decrease, it's originally 0.010 molar. If it decreases by 90%, I'm going to multiply that by 0.9. That's going to come out to be 0.0090 molar. That's how much was lost. So how much remains, we're going to subtract that out. 0.0010 molar is left. So we can use our natural log equation now. Natural log of 0.0010 molar is equal to negative KT plus ln of the initial, which is 0.01, right here. Alright, so natural log of 0.0010 comes out to be negative 6.91. Our K is given to us as 0.21. Notice the negative sign there. Times the time plus ln of 0.01, which is negative 4.6. Rearrange the equation and we get negative 2.3 is equal to negative 0.21 times the time. Divide both sides by negative 0.21. The time comes out to be 10.95. Now this is in hours. So that's how many hours it takes. Let's do a couple more. Determining the t of 1/2 when given k in the known rate order. Problem once again is sugar, and then once again is a first order process. The k is 3.3 times 10 to the negative fourth s to the minus 1. Notice this is a lot faster because we have an enzyme involved. What is the half-life of the reaction in minutes? So it's first order, so that means t of 1/2 is equal to ln of 2 over k, which is the same thing as saying 0.693 over k. The k is 3.3 times 10 to the negative 4. Divide that out, and it comes out to be 2100 seconds. But the question was asking for the answer in minutes. Make sure you're answering the question that's being asked. So I'm going to convert this to minutes. There's 60 seconds in 1 minute. So I'm going to divide by 60, and that comes out to be 35 minutes. And finally, let's say we still are dealing with sugar, and we actually have 5 grams to start with. Remember, sugar is a first order reaction, which means we still want to have ln of A is equal to negative kT plus ln of A naught. 5 grams is going to be our A naught. Determine how much sucrose is left after 2 hours and 20 minutes, which comes out to be 140 minutes. So ln of A, we're trying to figure out how much is left. So that's going to be our question mark. Negative k, which is 3.3 times 10 to the negative 4 seconds to the minus 1. Time, they gave it to us in minutes. They gave us hours and minutes, but our k is actually in seconds, so we need to make sure that matches up. 140 minutes, and for every minute there's 60 seconds. That comes out to be 8,400 seconds. Plus ln of A naught, which is the 5 grams. Alright, so let's do some calculations here. ln of A is equal to, these two things multiplied together is negative 2.772. Plus ln of 5 is 1.61. Add those together, and it comes out to be negative 1.162. Now we need to get rid of that ln so we can get the A by itself. In order to do that, we're going to do the e to the x function, and that breaks down that e. So that means we have A on this side, and then we have e to the negative 1.162 on the other side. And that comes down to be 0.313 grams. And that's how we use the integrated rate laws and how we associate it with half-lives.